Hello everyone, my name is Isaac Eskin and then you are welcome to the second part of our tutorial class in calculus. Now in this second part we are still looking at problems or questions that involves limit. In the first part we solved some questions involving limit, and in the second part we are continuing with it. Now in this part we have some problems here that we need to find or calculate the limit. So let's begin. Now in the first question we have to find the limit as x approaches infinity of x squared plus 1 all over x plus 2 multiplying 3x minus 4. Of course, we just need to expand the denominator, right? We can easily expand the denominator. So we have x squared plus 1. Now, x multiplying 3x will be 3x squared. X multiplying negative 4x will be minus 4x. Now 2 multiplying 3x will be plus 6x. Then we have 2 multiplying negative 4 will be minus 8. So the denominator now becomes this. We have 3x squared. Of course, minus 4x plus 6x is plus 2x. Then minus 8. Now when we have it in this form and we want to take the limit as x approaches infinity, this is limit at infinity. We look out for the highest power of x and we divide each term by that. So clearly we are going to have the limit as x approaches infinity. The highest power here is x squared. So I will divide each term by x squared. So in the numerator part, I'm going to have x squared divided by x squared plus 1 on x squared. Then at the denominator I'll have 3x squared divided by x squared plus 2x divided by x squared minus 8 also on x squared. And of course this will give us, now x squared cancels x squared, so we have 1 plus 1 on x squared. Then the down part to this x squared cancels this, we are left with 3 plus, of course 1x will cancel the x squared down here, so we have 2 on x, then minus 8 on x squared. And don't forget we are taking the limit as x approaches infinity. Now wherever we see x, we want to put x infinity there, but clearly you know that any number over infinity is 0. So on the numerator we are going to have 1, because 1 over infinity squared definitely is going to be a larger number, so we will get 0. Now at the denominator you will have 3 here. Of course this will also go to 0, because 2 on any large number will be 0, 8 on infinity squared, which will be very large, and that will also go to 0. So finally our answer becomes 1 on 3. Alright, now we move to the second part. We have to find the limit as x approaches infinity of root of x plus 1 minus root of x. Now here we don't just substitute the value of infinity. Of course infinity is not a number, it's a concept, right? It's a concept that we know. But with this, because we have some set here, we would want to rationalize. So we are going to have the limit as x approaches infinity of root of x plus 1 minus root of x. We are going to multiply this by the conjugate. So we will multiply this expression by the conjugate of this, both numerator and then denominator. So we are going to have root of x plus 1 plus root of x over root of x plus 1 plus root of x. Of course, don't forget that this is over 1. So finally, we multiply the numerator by numerator. We are going to have root of x plus 1 minus root of x multiplying root of x plus 1, plus root of x. That is for the numerator. Then the denominator, 1 multiplying this is just root of x plus 1 plus root of x. Of course, let's expand the top part, which is the numerator. Now if we expand, root of x plus 1 times root of x plus 1 will just be x plus 1. And of course we will have root of x plus 1 times root of x. Clearly you can see that if you expand this term, root of x plus 1 multiplying root of x, so you will have this. So plus root of x plus 1 multiplying root of x. Then you have minus root of x also multiplying root of what? X plus 1. Then minus root of x times root of x definitely is going to be minus x all over the denominator root of x plus 1 plus root of x. So clearly you can see that this expression cancels this expression. X also cancels negative x. And we are left with the limit as x approaches x approaches infinity of 1 on root of x plus 1 plus root of x. Then of course we know that infinity is a very large number. So if we take the square root of a very large number and add it to 1, we are still getting a very large number. And also if we take the square root of that same large number and we add it to this result, of course you can see that the denominator will be a very large number, and 1 over a large number will definitely be equal to what? 0. Or any number over a very large number is just 0. Alright, now let's look at the third question. Let me clean this space so that we can get space here. Alright, so now the third question says that we should find the limit as x approaches 0 of 1 minus cos x over x squared. Of course, if we didn't have x squared here, we could have just used the normal identity we know to say that the limit is 0, right? But this doesn't look like the normal identity that we have, which is the limit as x approaches 0 for 1 minus cos x over x, which is equal to 0. So this does not look like this, right? So we cannot use this. But I'm going to use this one to teach you a new concept in limit, right? There is a rule that we used whenever we are getting an indeterminate form. Of course, if I plug in 0 here, I'm going to have 1 minus cos of 0, and cos of 0 is 1. Then the denominator will be 0 squared, which is 0. So the numerator is going to give us 0. The denominator will give us 0. So we are going to get indeterminate form 0 over 0. So I'm going to teach you a new concept. Whenever you are having an indeterminate form, we use something we call the L'Hopital's rule. The L'Hopital's rule. So what does the L'Hopital's rule say? The L'Hopital's rule says that whenever we are evaluating the limit and then we are getting an indeterminate form, when we plug in the number, that is where x is approaching, and then we are getting an indeterminate form, then what we need to do is that we will differentiate the numerator separately and then differentiate the denominator separately. Then after that we can now take the limit. Now if we do that and then we are still getting an indeterminate form, then we need to keep on differentiating. Now mind you, you are not differentiating this whole expression so that you would want to use the quotient rule. No, you are just differentiating the numerator separately, and then you differentiate the denominator also separately. So we are going to apply L'Hopital's rule to find or to calculate the limit for this expression. Of course, so we are going to have the limit as x approaches 0. Now when I differentiate the numerator, if I differentiate 1, I'm going to get 0 because 1 is a constant, right? Then if I differentiate cos x, that will give me minus sine x. So I'm going to have minus the negative sine x. Let me clear this L'Hopital's rule from there. Alright, so when I differentiate 1, that will be 0, then minus. When I differentiate cos x, I'm going to get negative sine x all over. Now when I differentiate the denominator, which is x squared with respect to x, I'm going to have 2x, right? And of course, finally, I'll be taking the limit as x approaches 0 of sine x over 2x. Now, at this stage, if I plug in 0 into this expression, you will realize that we are going to get an indeterminate form again, because sine 0 will be 0 and 2 multiplying 0 will be 0. So at the end of the day, we are going to have 0 over 0. Right, so since we are still having an indeterminate form, we still keep on applying L'Hopital's rule. We are going to differentiate the top, and then we also differentiate the down, which is the denominator. So we are going to have the limit as x approaches 0. Now when I differentiate sine x, that will give me cos of x over, when I differentiate 2x with respect to x, of course that's just going to be 2. Now at this point I can evaluate the limit of this expression by plugging in 0, right? And if I do that, I'm going to have cos of 0 over 2. And cos of 0 is 1. So we are going to finally have 1 over 2. So the limit as x approaches 0 of 1 minus cos x over x squared is half. Now here what we did was we used the L'Hopital's rule. Just a quick recap. I said the L'Hopital's rule is used whenever you are having an indeterminate form. And then how do you use the L'Hopital's rule? You differentiate the numerator separately, and then you differentiate the denominator separately. Then you take the limit of that expression. If you do that and you are still getting an indeterminate form, you keep on differentiating the numerator and then the denominator separately until you are able to evaluate the limit. Alright, now the next one, in the next question, we have to find the limit as x approaches 0 of tan 3x over cos 5x. Now from trigonometry, you know that tan x is equal to sine x on cos x. So that implies that tan 3x is equal to sine 3x over cos 3x, sorry. So I'm going to substitute this expression in place of tan. That means we are going to take the limit as x approaches 0. In place of tan x, I'm going to put this identity there, this expression. So I'm going to have sine 3x on cos 3x. Now everything divided by cos 5x. And of course this changes to, so sine 3x over cos 3x times 1 over what? Cos 5x. Of course we take the reciprocal. And don't forget we are taking the limit as x approaches 0. And this is equal to the limit as x approaches 0. Of course sine 3x multiplying 1 will be sine 3x. All on. We are going to have cos 3x multiplying cos 5x. Then here we plug in our 0. Of course the numerator is going to be sine 3 multiplying 0. Of course that will be 0. So sine 0 on. Here we are going to have cos 3 multiplying 0 is cos 0. And then cos 5 multiplying 0 is still cos 0. And finally we know that sine 0 is 0. Cos 0 is 1 multiplying 1. And then finally our answer will be 0. So the limit of tan 3x on cos 5x as x approaches 0 is 0. Alright, let's look at the last one. The last question in our problem set. And we are done for this session. Now, with the last one, we need to use a special limit. Alright, so let's get to it. So we are supposed to find the limit as h approaches 0 of e to the power beta h minus 1 all on h. Now there's a special limit, and this limit is the limit as h approaches 0 of a to the power kh minus 1 over h. This is equal to k ln a. This is a special limit. So this is actually a special limit. Oh, sorry. So ln a. And this is what we are going to use to evaluate the limit above. Now notice that here, when we compare this special limit to the question above, our a is e and our k is beta. Hence, the limit as h approaches 0 of e to the power beta h minus 1 over h. Now, just as I said, as we compare this to this, we know that our a is e. And what is our k? Our k in this question is what? Beta. And you can find it. So we write beta ln, of course our a is e, so we have ln e. And you know from basic mathematics that ln of e is 1, right? Why is it 1? The ln is the natural log, and the natural log has the base e. So this is simply log e to the base e. And of course, from the log property, you know that this is 1. So the final answer becomes what? Beta, because ln e is 1. I hope you enjoyed this session as well, and please make sure you do subscribe and then like and then share this video as well. I will come your way with other problem set where we'll also look at continuous functions and then derivatives of functions. Thank you very much for having me tonight.